Hello and welcome to the first of the lectures in this week 10 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In this lecture, we will look at a concept termed as the extensionality of a fuzzy set. Before moving to this concept, let's make some interesting observations. Let us consider a single seesaw rule, single input, single output rule, and let's use this in the CRA inference mechanism. Of course, in this case, either if you use the theta or the fatty inference strategy, both are same because we have only a single rule. So let's assume that we have a rule A implies B, and since it is CRA, we have to use a sup T composition. For that, we have taken the minimum sup min composition. And the operation F is required to obtain the relation from the rule, for which we have taken the Gödel implication. Let's assume the rule is A1 implies B. A1 is given as this fuzzy set 1.3.3 and B is 0.4.8. Now, we know that we obtain the rule using this implication F, the Gödel implication. So quickly, how do we do this? We have this 1.3.3, use the Gödel implication, 0.4.8. Please recall the Gödel implication is this: 1 if x is less than or equal to y, and y if x is greater than y. So put together 1 and 0.4 mean 0.4 because it's a neutral implication. 0.3 is smaller than 0.4, which means 1. 0.3 is smaller than 0.8, 1. So you get this. So you see here, that's how we have got the relation from the rule. Now, the first interesting question to see is this interpolative? Well, we know this because minimum, and we are using the corresponding residual implication, and there's only one single input here, rule here, which is also normal fuzzy set. So perhaps you suspect it will be interpolative, and as can be verified, yes, indeed it is interpolative. Now, what is interesting is this. Let's look at the input-output mapping for some arbitrary fuzzy sets. Let's give this as the input to the system. That means given A star, we are going to compose it with R cap and see what the output that we get is. Now, clearly, if this is the input, 0.9, 0, 0.3, compose it with sup min with R cap, which is this. Clearly, we are doing sup min composition. So the first component is minimum of, maximum of, min of 0.9 and 0.4, 0 and 1, 0.3 and 1. So max of this and max of 0.9 and 0.8, 0 and 1, 0.3 and 1. Clearly this will turn out to be this quantity here, which is 0.4, and this quantity here, which is 0.8. So this is actually equal to B. So the point is not that it is equal to B. The point is this is the output we are getting. Well, now what we'll do is we'll give another input which is slightly different. So you see in the middle component it is 0.3. And if you do the same calculation, we still continue to get the output as the fuzzy set 0.4, 0.8. Now, let's change the input to something else, 0.7, 0.2, 0.3. And if we give this as the input to the system, the output is 0.4, 0.7. We are not discussing interpolativity here because it is not actually A1. But what is interesting is, if you slightly modify this, instead of 0.2, if you use 0.3, we still obtain the same output 0.4, 0.7. So even though A star and A star cap are different, we obtain the same outputs from it. And once again, A sub star and A sub star cap, even though they are different, we obtain the same output 0.4, 0.7. Now you might suspect it is probably because we have an interpolative system. Well, let's look at another system. We will retain the same consequent B, but we'll change the antecedent to this fuzzy set A2, which is given as 0.6, 0.3. Once again, using the Gödel implication, we see that this is the relation that we would get. Is this interpolative? Well, if we work out, we will see the output is 0.4, 0.6, which is not equal to B. So this system is not interpolative. Let us give the same input A star, which is 0.9, 0.3, to this system and look at what we get as the output. Of course, it is not the same as B as we got earlier. However, as we said, the point is not what exactly is the output that we get. The point is about if we give two different inputs, are we getting the same output? And we see here, by giving this pair of inputs, we actually get the same output. Now, what about the other pair of inputs? Once again, we see that for this input 0.7, 0.2, 0.3, 0.4, 0.7 is the output, and so is the case when the input is 0.7, 0.3 and 0.3. Well, now this system is not interpolated. So what could be playing the role of ensuring that for these inputs we get the same output? Once again, we know the power of residuated lattices. So we may suspect, okay, we have the minimum T norm here and we use the corresponding R implication, which is the Gödel implication. Perhaps this pair is playing the role. Can be. So let's put that theory also to test. So let's change the sup T composition from sup min to sup Lukasiewicz T norms composition, but still use the same Gödel implication. And once again, we are going to use the same antecedent A2. Even with this changed composition, it is not interpolative. Let's give the same inputs. Quite interestingly, we find that for this pair of inputs, once again the outputs are same, and for this pair of inputs, again the outputs are identical. The next thing that you would think is perhaps it is the R cap relation that is playing a role. So once again, let's put this theory to test. Keep the composition to be sup Lukasiewicz, same fuzzy sets, but let's use the minimum T norm to obtain the relation. So we are looking at it as positive rule. And if you give A2 to this, we don't get B, so it is not interpolative. Why only TM? Why not also TLK? So let's use the Lukasiewicz T norm also to obtain the relation. And once again, we see that it is not interpolative. So there is no relation in terms of the residual operation between the composition operation that we are using and the operation F that we use to obtain the relation from the. Now we'll see we in fact increased the distance, so to speak, between A star and A star cap, but we still seem to be getting the same identical output. What about for the other pair of fuzzy sets? Once again, instead of taking it to be 0.3, 0.3, we have pushed it even further to 0.6. And what we see is that the outputs from these two inputs are in fact identical. Now, is this magic? Will this happen always? Is this an artifact of the operation that we are employing? Or is this an artifact of the numbers that we have considered? Or is there some insightful gain in knowledge looking into this a little deeper? Also, the question is, will this always happen? Now let's look at this. This was the first system that we considered, interpolative, and we gave these as the inputs, these two pairs of fuzzy sets as inputs, and we got identical outputs for each of the pairs. Now what we'll do is we'll slightly tweak this. We give this as the input, 0.9, 0.2, 0.5. This is the output, and we have only modified it slightly. We have not gone further ahead, but we see that the outputs are different here. So is the case here. We only changed one component from 0.5 to 0.6, and we immediately see that even for the original interpolative system that we considered, the outputs are different. So clearly, there is something else at play here, and this is what we want to understand. Because remember, we are not looking at this from the fuzzy relational equations point of view. No, we are looking at it as having a system, and given an input, we are obtaining an output, and we are only interested in seeing there is a phenomenon that is happening where two different inputs are giving us identical outputs, and this seems to happen even when we consider different operations, different antecedents. So it would be gainful to look into this little deeper. Now, towards that end, let's look at the concept of extensionality of a fuzzy set. For that, let's revisit what a T-equivalence relation is. A T-equivalence relation is a binary relation on X, a fuzzy binary relation on X, which is reflexive, symmetric, and T-transitive. Now, we know that if a relation is Tm transitive, then it is also T-transitive for any T norm, because, for instance, if it is Tm transitive, then what we have is min of E of xy, E of yz is less than or equal to E of xz for all xyz element of x cube. But we know minimum is the largest T norm, so any other T norm if you use, by monotonicity it will be smaller than this, which means any E which is Tm transitive is also T transitive for any other T norm. Of course, the converse is not true. We can find examples. Now, for the rest of the lecture, once again, for this week also, we'll assume that when we discuss the case of CRI or BKS, that means as long as we are in the realms of fuzzy relational inference, we will consider the operations to come from the corresponding residuated lattice. That means the T and IT are related as T norm and the corresponding residual implication, and often we will also use the infix notation to make the notation simpler. Now, we have seen in one of the lectures in the last week that by implication can also be seen as an equivalence relation. What's a by implication? X by residuum of by implication y is minimum of x implies y, y implies x. In the case this implication comes from a residuated lattice structure, we know that E of xy defined as x double implies y or y implies y is in fact reflexive, symmetric, and star transitive, where star and implication are coming from the residuated lattice structure. It's a star equivalence relation. Now recall, if you consider the minimum T norm, the corresponding R implication is the Gödel implication, and using this definition of a biresiduum, we get that the EM, means M min transitive fuzzy relation EM is given like this. If you consider the Lukasiewicz T norm, the corresponding Lukasiewicz implication, the biresiduum of that is essentially this. So getting the equivalence relation from there would look like this. The LK would be 1 minus mod x minus y, mod of x minus y. So for the moment, let's consider that x consists of these three values, 0.3, 0.6 and 0.9, and the equality relation, the equivalence relation EM on this using this formula can be obtained for the set X which consists of these three values. Clearly 0.3, 0.3 is 1, 0.3, 0.6, minimum of them is 0.3, 0.3, 0.9 is 0.3, 0.6, 0.9 is 0.6. So this equivalence relation is easy to obtain. For the same set X, if you obtain the equivalence relation ELK, this is how it would look like. 0.3, 0.3 is 1, 0.3, 0.6 is 1 minus, the difference is 0.3, so that is 1 minus 0.7, 1 minus 0.3 which is 0.7, and when we put 0.3 and 0.9 here, the difference is 0.6, so 1 minus 0.6 is 0.4. So these are the corresponding min equivalence and Lukasiewicz equivalence relation that we can get on this set X using these two formulae. Of course, there are many other equivalence relations which can be min transitive. For example, we have seen that EM, it is min transitive, which means it will also be LK Lukasiewicz transitive, product transitive, every T norm in fact. It will be T transitive with respect to every T norm. Now, let's look at what is extensionality of a fuzzy set. Let us be given a star equivalence relation on X, means E is reflexive, symmetric and star transitive. If we take a fuzzy set mu on X, it is said to be extensional with respect to E if it satisfies this particular property. What does this say? If you take an X and Y, mu of X star E of XY should be less than or equal to mu of Y. Remember, E is an equivalence relation, in some sense equality relation or similarity relation. We have also seen that it is strongly reflexive. That means E of xy as obtained, if it is obtained from the biresiduum operation, we know that E is strongly reflexive. That means E of xy is 1 if and only if x is equal to 1 is equal to y. So in the general case, x and y can be different, but let's assume that E of xy is actually equal to 1. That means with respect to this equality relation, x and y are in fact indistinguishable. For that equality relation, they are indistinguishable. So now all it says is, if x and y are indistinguishable, then what should be the value of the membership value of y in this fuzzy set, in this concept mu? It says it should be at least as much as x. And clearly, because of the symmetry of E, we could also write it as mu of y star E of y comma x less than or equal to mu of x. And if xy, E of xy is 1, then E of yx is 1. We see that mu x is in fact equal to mu y. So this is one way of ensuring that if x and y are indistinguishable with respect to the similarity relation or the equivalence relation E, then they should have the same membership value in that concept represented by mu. So this is the main idea behind defining extensionality like this. So let's look at the relation EM, which we know is a min-transitive fuzzy relation. And let's look at some fuzzy sets and see whether they are extensional with respect to this relation. We will see whether they are extensional with respect to, remember, this E can be any equality relation. We are only going to talk about E, this mu being extensional with respect to E and this star, because E is star equivalent for us. And since this is TM equivalent, so this will be T equivalent for any T now. So we could consider the extensionality of a fuzzy set with respect to this relation with any T now. In particular, we are going to consider the min T now and the Lukashevich T now. Let's consider the first antecedent that we took, A1, which is 1.3.3, and ask the question, is this fuzzy set extensional with respect to E and the T norm Tm? So what does this mean? If A1 is given, we need to show A1 of x star, here the star is min, Em of xy should be less than or equal to A1 of y. And this should happen for every one of them. Now, what is A1? So now we have x to be x1, x2, x3. A1 is 1.3.3. So now if we take A1 of x, then it is 1, and Em of x1 should be less than or equal to A1 of x1. Clearly this will happen because x1 is 1, this is 1. So for the diagonal elements we don't need to check. So let's arbitrarily take A1 of x3 and Em of x3, x1. This should be less than or equal to A1 of x1. Now A1 of x3 is 0.3, and what is Em of x3, x1? So this is x3, x1, it is also 0.3. This should be less than or equal to A1 of x1, which is 1. So this is true. But we need to check this for all possibilities. So the easier way is to write something like this. Let's write A1 star, in which case here it is this, and let's put Em here, which is 1.3.3, 0.3.3, 1.6, 1.6, and let's take each of these and multiply with the corresponding row. So perhaps it is easier to write it as a column vector, 1.3.3. So now all we are going to do is take 1 and multiply with this, because this is x1 for us. So this is x1, this is x1, x2, x3. So x1 into E of x1, x1, x1 into E of x1, x2, and see whether it is less than or equal to the corresponding A1 of x1 or x2 or whatever we write here. So this, if we take it as this matrix, so now we are using minimum here, 1 and 1 is 1, 0.3, 0.3, 0.3 and 0.3 is 0.3, 0.3 and 1 is 0.3, 0.3 and 0.6 is 0.3. Similarly, 0.3, 0.3, 0.3, 0.3. Now, what do we need? We simply need that if we write A1 here itself, we need that the max of this should be smaller than this. So for each one of them, because remember what is this? Well, let's fix this. This is A1 of x2. What we want is it should be smaller than A1 x1 star E x1 x2 x1 x1 A1 x2 star E x2 x2 and A1 x3 star E x3 x2. So it should be smaller than all of them. And what is this value? This value is 0.3 for all of them. Now, what is this A1 x1 star E x1? It is essentially x2 x1 x2. So this is this value. This value is, this entire thing is here, and this entire thing is 0.3. So it's easy to just find the matrix and look at, if you write the same set on top, the fuzzy set, it's easy to see that this element dominates, each of these elements dominates the column. That means it's bigger than all the elements in the column, which means this set is in fact TM transitive, extensional. So given A1, this is extensional with respect to min, EM and min. That means it is also going to be extensional with respect to the Lukasiewicz. It can be checked. Now, let's consider A2. So we need to do the same thing again. Let's write A2 like this, 0.6, 0, 0.3, and we consider min, so 0.6, min 1 is 0.6, 0.3, 0.3, 0, 0, 0, 0.3 in this row, 0.3, 0.3, 0.3. Now if you write our A2 here, 0.6, 0, 0.3, it can easily be seen that the max of this is 0.3. They are all not smaller than this. Note that. Simply take like this. A2 of x2 star E of x2 x2 is it less than or equal to A2 of x2? A2 of x2 is 0 star, we can just take A2 of x1 x2. A2 of x1 is 0.6 star E x1 x2 is 0.3, and the star is minimum, so this is 0.3. Is it less than or equal to A2 x2? A2 x2 is 0. It is not, so this is not extensional. So this fuzzy set is not extensional with respect to the min T norm. So it is not extensional with respect to EM and min T norm. Let's look at what happens whether it is extensional with respect to the Lukasiewicz T norm. So once again we write it like this, 0.6, 0, 0.3. Now star is the Lukasiewicz T norm. EM is same, 0.6 and 1. Now note that we are going to use the Lukasiewicz T norm. What is the Lukasiewicz T norm? It says TLP of xy is max of 0, x plus y minus 1. Now 0.6 and 1 is 0.6. 0.6 and 0.3. 0.6 plus 0.3 is 0.9, which is minus 1 is negative, so it is 0. Once again 0.6, 0.3 will be 0. 0 will always be 0. 0.3 and 0.3 is 0.6 minus 1 is minus 0.4, so which means it is 0. 0.3 and 0.6 is 0.9, which is less than 1, means 0. And finally 0.3 and 0.3 is 0.3 and 1 is 0.3. So now you see here, this is what we get. If we write out the corresponding A2 here, 0.6, 0, 0.3, we see that this is dominated by 0.6, this is dominated by 0, this is dominated by 0.3, which means this set is in fact, this fuzzy set is extensional with respect to EM and the Lukasiewicz t-norm. Now, if you consider this fuzzy set, it can be easily verified. It is not extensional with respect to EM and min. However, it is extensional with respect to EM and TLK. Now, let's consider the last of them, which is 0.9, 0.3, and consider whether it is transitive with respect extensional with respect to EM and the min operation. So what we have is 0.9, 0.3. This is the t. What we want to do is take 1, 0.3, 0.3, 1, 3, 0.3, 1.6, 1.61. So we see that we are essentially taking the min operation. So it is 0.9, 0.3, 0.3, 0, 0, 0, 0.3, 0.3, 0.3. So now, if we write out the corresponding 0, 0.3, we see that this is not less than this. So this is not extensional with respect to TM. Is it extensional with respect to the Lukasiewicz t-norm? Let us look at that also. So all we are going to do is change this into the Lukasiewicz t-norm. So allow me to write it here. This color. 0.9 and 1 will be 0.9. 0.9 and 0.3 will be 0.9 plus 0.3 minus 1. 1.2 minus 1, which is 0.2. So this is also 0.2. 0 will give you 0 throughout. 0.3 will be 0. 0.3, 0.6 will be 0. This is 0.3. So now what we have here is, if you write 0.9, 0, 0.3, you see that this is dominating it. This is not dominating it. 0 is not greater than this. This is dominating, okay. But 0 is not greater than 0.2, which means this is neither extensional with respect to EM and min, nor is it extensional with respect to EM and the Lukasiewicz t-norm. So this is what we have here. Now the next question is, if a fuzzy set is not extensional with respect to a given equivalence relation, can we make it extensional? Well, let's begin with a star equivalence relation on X and let mu be given fuzzy set. The extensional hull of mu is given like this. What do we do here? We take all those mu which are greater than mu, and mu is also extensional with respect to E and the star that we have fixed. Among all these mu's, we actually pick the smallest one. So put another way, the extensional hull mu which we of mu, which we denote as mu cap, is the smallest extensional fuzzy set mu which contains mu. So first of all, it should be extensional with respect to E, it should contain mu, and it should be the smallest one, so the infimum of all of them. So the smallest extensional fuzzy set with respect to E which contains mu. Now this is something like an external characterization of how to obtain an extensional hull when you are given a mu. For instance, we know that if we have a vector space V and if you are given a subset E, we can ask the question, what is the subspace that E can generate? What is the subspace that E can generate? There are two ways to denote this. For instance, the external characterization is the subspace. Let's denote this subspace obtained from U as U, from E as U. We can say this is all those subspaces U1 such that U1 contains E, and take the intersection of them. We know that arbitrary intersections of subspaces is a subspace. So this is, consider all the subspaces U1 containing E and take the intersection. Another is to say that U is equal to L of E. That means it's essentially the linear span of E. Essentially what we are doing is taking different vectors from E, multiplying them with different scalars from the underlying field and adding them up. And all possibilities that we consider and put them inside, and that is how we grow it. So either externally we take all the bigger ones and find the smallest one, or you grow it from inside. So in that sense, this definition is the external characterization of what an extensional hull is. But how do we find all the extensional fuzzy sets with respect to E that contain mu and then to obtain the infimum? So this is where the following definition comes in handy. It says mu cap given a mu is nothing but given like this: the supremum of mu y star EYX for every y. So essentially, if you look at it another way, succinctly put as mu cap is nothing but mu circle star E that you have considered. Let's go ahead and prove that this mu cap is in fact the extensional hull. So what we are given is mu cap of x, and we are given a supremum x element of x, y element of x, with that mu y star E of yx. That is what is mu cap of x. So to show that this mu cap is given like this, so let's denote the right hand side as mu tilde of x. We need to show two things. Firstly, that mu tilde x is extensional with respect to, and write it as E comma star. That's the first thing that we need to show. The second thing that we need to show is that if mu is some other extensional fuzzy set and contains mu, then we need to show that mu is actually contained. Mu contains mu tilde. So we want to show this is the smallest mu contains mu tilde. So mu tilde is essentially the smallest extensional set with respect to E which contains mu. Oh, let's prove one. To prove one means we need to show mu tilde of x star E of xy is less than or equal to mu tilde of y. Let's look at the LHS. This is mu tilde of x is supremum over T element of x, mu of T star E of Tx star E of xy. Now, this is supremum over T and this is star. We know that star is a T norm. It's coming from a residuated lattice, which means it is in fact left continuous. That means it is supremum preserving. So we can simply push this inside. What we have is supremum of T element of x, mu of T star E of Tx star E of xy. Now, because of associativity, we do not need to put any brackets. But if you consider this fellow, we know that E is a star equivalence relation. That means this term is in fact less than or equal to E of Ty. So overall then what happens is this less than or equal to T element of x, mu of T star E of Ty. Now this is essentially the definition of mu tilde of y. Note that what is mu tilde of y? Mu tilde of x, supremum over y element of x, mu y star E of yx. So this is essentially the definition of mu tilde of y. And what we have shown is that this quantity is in fact less than mu tilde of y. So mu tilde is extensional. So that's the first point we have shown. So let's also show the second point. So what are we given? We are given mu is greater than or equal to mu, and mu is extensional with respect to E and star. So now mu is extensional means mu of x star E of xy is in fact less than or equal to mu of y. But we know mu is greater than mu, so this implies mu of x star E of xy is less than or equal to mu of y. Now this happens for every x, so which means we can put sup over x here. It's still true, but this quantity is essentially of mu tilde of x, mu tilde of y, because y is fixed. So what we have shown is mu tilde is in fact smaller than mu of y for any arbitrary y in x, so which implies mu tilde is less than or equal to mu. Note that mu was originally extensional. We have shown that mu tilde is extensional, and we have shown that if there exists any other extensional fuzzy set mu which contains mu, then it also contains mu tilde. In that sense, by the definition of mu cap, we see that mu tilde is in fact equal to mu cap. So what we have managed to do is that we have given an internal characterization representation of mu cap, and this is how we obtain the corresponding extensional fuzzy set. So let's work this out. We have seen that, note here, so we saw that 0.9, 0.3 with respect to EM and min, it was not transitive because it is 0. This is the thing. It was not extensional. Now let's find the extensional of this with respect to the same relation. So all we need to do is take mu circle EM, and here this mu is in fact what we consider as D. So 0.9, 0, 0.3 circle min EM. Now this will be equal to sup min 0.9, 0.3, 0, 0.3, 0.3, 0.3, 0.3, 0.3, 0, 0.3, which is 0.3. So if you consider this as D, then this is our D cap. So now we have this mu cap. We have shown that this mu cap is extensional with respect to E, and in fact mu double cap is in fact equal to mu cap. Now what does it mean? If you take the extensional hull of extensional hull, then clearly it is equal to the original extensional hull. Now let's come back to the observations that we made. Now this is an interpolative system. We saw that for these two inputs, the outputs were same. Now we see something familiar. We have seen D to be 0.9, 0.3, and that is A star, and A star cap is 0.9, 0.3, 0.3, which is essentially the extensional hull of A star. And we see that whether we give this A star or its extensional hull, we seem to be obtaining the identical outputs. Once again, it can be verified that 0.7, 0.2, 0.3 is actually not extensional with respect to this R cap and minimum T now, but its extensional hull is in fact 0.7, 0.3, 0.3. And once again we see that we get identical outputs. And when we look at these two fuzzy sets, we can once again see that they are not related to each other as extensional hulls. So these two, they are not related to each other as extensional hulls, and we get these as different outputs. Now this gives us some insight in showing that perhaps it is extensionality of fuzzy sets which is playing a role here. We will look into this a little deeper, and that is how we will go up to the concept of robustness in the next lecture. So a quick recap of what we have done in this lecture. We have seen that often different inputs can lead to identical outputs. We ask the question why. We have to answer it, and we will also have to answer when they will be identical. This is something that we will take up in the next lecture itself. Towards this end, we discussed the concept of extensionality of a fuzzy set with respect to a equivalence relation and the operation star. And in the case a fuzzy set is not extensional, we have seen how to infuse extensionality. We have defined what is an extensional hull, and we have also seen some examples. Going forward, we will define what is robustness of an FRI as we understand, and in particular we will look at the robustness of both CRI and BKS. In the next lecture, we will concentrate on the robustness of the compositional rule of inference. The topics covered in this lecture are very well captured in this paper, a seminal work by Clavon and Castro almost 27 years back, wherein they proposed this entire idea of extensionality and showed what happens to inferences, especially CRI, when you have different inputs related to each other in terms of extensionality, how they give out identical outputs. And this is what we will be looking into in the next lecture, when we discuss the robustness of CRI. Glad you could join us for this lecture and hope to see you soon in the next lecture. Thank you again.